In this video, we're going to talk about practical skills, distillation and reflux. This is one of a few practical skills videos which take you through exam style questions and takes you into the lab to show you how to synthesize and purify an organic compound. So, first of all, let's look at the processes. So the processes are, first of all, you synthesize the compound, then you purify it, and your methods of purification are going to be either recrystallization or distillation. Okay, but let's go on with the synthesis first. So the synthesis is going to be a two-stage synthesis in your exam, but we will take you to more than 2 stages because we want to prepare you for that A star. We want to get to that A star, so we want to make it challenging so that you find 2-stage synthetic routes, frankly, really easy. Okay, so after we've done the synthesis, we can, not always, but we can go straight to a purification technique where you use a separating funnel. And as said, there is a video on this as well. You won't always need to do the separating funnel section though, but we'll explain when you do in the corresponding video. So from that separation, or not, you then go to the final stage of purification. This final stage is either with recrystallization, you see there's a beautiful crystals of copper sulfate here, okay, and you recrystallize it with a solid product. So if you have a solid product, something that has a melting point above normal room temperature, you can usually recrystallize it, and we'll go through how to recrystallize it in another video. Now, if you have a product that has a melting point that's less than room temperature, which means it's already melted and is an oil or a liquid, you tend to use distillation. So we'll go through all of these different stages and make sure that you can apply those to the exam questions you're going to get. Okay? But to start off, we'll just go with how do you do the synthesis. Okay? There is another video that goes through synthetic routes and how to do synthetic routes and work out what the synthetic routes are, but this one is about how do you do it practically in the lab and how do you answer the level of response questions that you're going to get in synthesis. And there's 2 ways of doing that, and that is reflux and distillation. We're going to start off though with distillation. So distillation is how you make aldehydes. So it's about the oxidation of primary alcohols to make aldehydes. And that's the most common way you use distillation in terms of reacting your substances together. You can also use distillation at the end to purify your substance, but we're talking about doing the reaction and having distillation as part of the reaction. So your oxidizing agent in doing this is acidified potassium dichromate, or as put here, Cr2O72- 4/H+. That can be represented as O in square brackets, and our example here is propan-1-ol, primary alcohol, because the OH is on the end of the chain. You add it to your oxidizing agent, and you distill, and then you make your aldehyde. That only takes 1 oxidizing agent to go to the aldehyde, and in the process of going from the primary alcohol to the aldehyde, you've lost these 2 hydrogens. Those 2 hydrogens get oxidized, so 2 hydrogens oxidized becomes water. Okay? Just to finish off, color change you've got to remember is orange to green, and we're just going to make it look nice by putting our reactants under the arrow. Now what we're going to do is take you into the lab and show you practically what this distillation looks like. So we're now in the lab to do oxidation of a primary alcohol to form an aldehyde. The primary alcohol we're going to use is 2-methylpropan-1-ol, and we're going to use dichromate, the Cr2O72-, which has this vivid orange colour, which you have to remember. Now this orange colour, when it is oxidizing the alcohol, is going to go to green. And hopefully you'll be able to see green when you look at this reaction which we set up here. So what we've got here is our dichromate, our alcohol in there, and we're boiling it, and it is evaporating up the tube. Now, here's the important thing. I'm going to show you some boiling points, and as you can see, the aldehyde has a boiling point of 63 degrees Celsius, whereas the alcohol and the carboxylic acid, which are the other 2 reactants and products that can occur in this, they are higher, 108 and above. So that means as long as we boil this to below 108, will only collect aldehyde. And the reason is because aldehydes have permanent dipole-dipole attractions between them, and they are weaker than hydrogen bonds. And the alcohol and the carboxylic acid have hydrogen bonds, therefore their boiling point is higher. So we can use that to our advantage to be able to get the aldehyde off because it has a lower boiling point than the other two. So if we then look at this, we can see it is evaporating, going up the tube, and we can see that our temperature that we've got on our thermometer is less than 108. So we are only going to collect the aldehyde. And then if you look here, it is condensing down this tube in the condenser, and then it is turning into a liquid in the ice bath. And the ice bath is just to make sure none of it escapes as a vapor. Now that is how you distill to make an aldehyde from a primary alcohol. And now we're going to go back into the studio to show how this can be drawn and done in the style of an exam question. Now you've been in the lab and seen all of these different apparatus added together to make distillation, you now need to know how to draw it in an exam if you're asked in a level of response type question. So let's put all this together. So when you put it all together, you can see that you've got, as we saw in the lab, you've got your round bottom flask, which you need to label. So it's really important you label that. Your thermometer needs to be labelled, your reflux condenser and ice bath need to be labelled. So they can be mark worthy in a level of response question on this. You're going to design a practical to synthesize ethanol from ethanol. So as we did in the lab, the distillation. And what makes it possible is, if you look here, this has the lowest melting point. Because it has the lowest melting point, as you heat, that means that only your ethanol will be boiled off and your ethanol and ethanoic acid will stay in the round bottom flask as long as you make sure the temperature does not exceed 78 degrees, because then the ethanol will start to boil off. So we start off with our ethanol and our ethanoic acid in the round bottom flask, and we heat it to less than 78. So it doesn't matter what temperature we take to, but if we're stating in the exam, we have to state a number less than 78. We allow that to react, and we can see the colour change going to green. Okay. Also, mark worthy as you come over here is your water is going in at the bottom and it's going out. And again, it's important here that it's pushing the bubbles out of the jacket, which is why you go in at the bottom and out at the top. Okay. Now, as you heat then, you'll find that your aldehyde, as you can see from the arrows here, is going into the ice bath, and you get ethanol in the ice bath. Question you may need to answer as part of this LOR question is, why do we only produce ethanol? It's because the ethanol escapes and separates from the oxidizing agent. Okay. Now that means it's not oxidized any further because it's escaped from here. If it stayed in here, it would continue to oxidize to the carboxylic acid. Now we're going to move on to reflux. Okay, and reflux in two examples: oxidation of alcohols to a carboxylic acid, which is a primary alcohol to a carboxylic acid, and using reflux to oxidize to a ketone. So that primary alcohol to carboxylic acid, if we take this primary alcohol here, again, which is same as before, propan-1-ol, okay, and this time we need two oxidizing agents, because one oxidizing agent to turn it into the aldehyde, and then the second oxidizing agent to turn it into the carboxylic acid. But at the same time, if you look at the difference between the reactant and the product, you can see that there is two less hydrogens on the product, okay, than there is in the reactant. So those two hydrogens have left, and therefore they're oxidized, making your one water. And to finish off, as always, the color change is orange to green. Now, if we're thinking about this in terms of ketones, we have to start this time with a secondary alcohol. So this is our secondary alcohol, propan-2-ol. You add the oxidizing agent to it, and then you will make your ketone. So we can see our ketone here, this C-double-bond-O with the R groups either side. Now if you notice again, there is two hydrogens that are missing. So two hydrogens have been removed and they are oxidized, so you get one water. And as we've said all the way through, colour change is orange to green. But now I'd like to take you into the lab to see how you would set up this apparatus to do reflux for both a secondary alcohol to a ketone and for a primary alcohol to a carboxylic acid. In this video, we're going to do an example of reflux. Now, the example we're going to do is the oxidation of a secondary alcohol, propan-2-ol. So we have propan-2-ol here. See, it's a colourless liquid. And then we have our oxidising agent. Our oxidising agent is acidified potassium dichromate. And you can see this is orange. Okay, you will need to remember that colour change that we have during this experiment. And it is cancer-causing, hence I've got gloves on. Okay, and it's really important if you do this in the lab. You've got the lab coat, you've got the goggles, and you've got your gloves on. We're also going to use anti-bumping granules to make sure the liquid doesn't bump up the tube. So, what we have is propan-2-ol, and we can represent our oxidising agent with square brackets and O, and then that makes our ketone and also makes water. And that's your balanced chemical equation that I would expect in the exam for this reaction. Now let's move on to the actual condenser itself. If we're drawing this, we're going to have to label the condenser, we're going to have to label the round bottom flask, and when we go into the next version of this, when we're heating it all up, we'll have to label the heat as well. But before I do that, I want to show you the water in and water out. So the water in is at the bottom. And what happens, and I'll show you right here, is as I put the water on, you'll see that the water goes up and then it forces all of the air out. And that's what you want it to do. And I'm going to put it on a bit stronger just to force all of the air out. There you go. You can see all that water is now forced out. And then I'm going to put the flow right back down so it's really, really small. You can see this outer kind of casing is full of water now. So it's very, very cold and there's no air bubbles, and that's why we fill it in from the bottom. So if you're doing the exam, water in from the bottom, water out from the top. So what we're going to do now is we'll put all of our chemicals into our reflux apparatus and show you the full setup. We've now done the whole reflux setup. You can see that we have our heat-proof mat, we've got a tripod and a water bath. And you often use a water bath. You can also directly heat it with a Bunsen burner, but you have to be really careful with that. And we are heating it using that Bunsen burner to get this evaporation and this condensation. So it's evaporating from here, and then you can see it condensing as well. Now, really important thing is that when you're drawing this in the lab, you can draw that Bunsen burner as an arrow and just write heat by it. You don't have to draw the Bunsen burner, and then obviously you have to label the round bottom flask and the condenser and your water in at the bottom, water out at the top. Okay, but the really important thing here is that why do we do this reflux? We do this reflux to make sure that the reactant doesn't get away from the oxidizing agent, so it's fully complete, the reaction is fully complete, and we also do it so that the solvent can't escape because it evaporates and then condenses, and solvents are often flammable, so it's much, much safer to keep the solvent trapped within there. And those are two reasons why we use reflux. In this case, we want to push that propan-2-ol all the way up to propanone. We want all of it to react, so therefore we choose reflux to keep all of those reactants together. What we're going to do now is take you back to the studio, and we will show you this in the form of an exam-style question and answer. We're now going to show you the details of a reflux exam-style question. We've got all our apparatus here, and we're going to need to make a diagram of that for this question. So let's make a diagram of reflux. We've made our diagram of reflux, and we decided to attempt a question on synthesizing propanone, which is a ketone, okay, from propan-2-ol, which is a secondary alcohol. Before we carry on to design the practical, we're going to do an equation with the practical and then explain why we're doing it with reflux. So here we've missed something off the diagram. This is mark-worthy, reflux condenser. This is mark-worthy, the round bottom flask. But what's also mark-worthy is the water in and the water out. Remember, that goes in at the bottom to push all the air out so that we get a nice cold jacket surrounding our tube so that none of the reactants or product escape. Now, let's have a look and see what we can do for the equation. So we're adding acidified potassium dichromate, which is orange, as you can see that come across there. And we're going to do our balanced equation. So I'm going to do it in skeletal formula. And there you have your there is your propan-2-ol. Now hopefully you're seeing now and thinking, how many oxidizing agents do I need to have? So I've put my oxidizing agent in to do my balanced chemical equation. Okay, and then I'm going to make my propanone. So my propanone is like that. Now, I'm doing it skeletal because I want you to get used to using the skeletal. There is a hydrogen here that is going to leave. You can see it leaving, but there is also a hidden hydrogen. I'll draw it in blue because you wouldn't normally put it in, okay, but there is a hydrogen here as well, and that hydrogen here and this hydrogen here, let's do that in blue as well, okay, and both of those are going to leave, and that means they leave, and then they get oxidized by the oxidizing agent, and you have H2O, okay, but of course we wouldn't normally draw this H because it's skeletal. Now, just to finish off, okay, let's put the reactants in. So that means we've got acidified potassium dichromate, which is, there you go, and we are going to do this as reflux. So mark-worthy points. So balanced chemical equation is always necessary in these kind of things, and you have your diagram. Now from that, they may ask you and say, why do you use reflux? So, or why do we only produce propanone? Now that is because the propan-2-ol is oxidized as it is always in contact with the Cr2O7H+. It never leaves, and if it never leaves, okay, it means it will fully react, and then this colour change will go to green. Now if it fully reacts, okay, that's great, but also at the same time, a lot of this stuff in organic is flammable, and so therefore, when it goes up the tube, okay, as you can see the arrow here, we don't want it to continue going out, it would be dangerous. So what it does, it hits this cold jack, it turns around, and then comes back down again. And we get this kind of reflux thing that you saw in the video. Okay, and that stops the reactants and products escaping, which is another good benefit of reflux and why we do it. Okay, and now this reflux is that evaporation, as I've shown there, and condensation, and stops the solvent drying out as well because that can't escape, which means that you can keep things nice and liquid as well. But the most important thing is they never escape because of this cold water jacket.